Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4, cameras on, 2, 1, release.
Setup, if I drop an object from this point, let's say this point, and here I place the stopwatch. Here I place the another switch. That means if I drop this, I can easily get the time for this object to fall all the way down here. That means the time of fall is known. And also we know the initial velocity because I said I'm going to drop it. And of course it's a case of free fall, so the only value of force is mg, so the acceleration is g, and by the help of this scale we measure the distance d. So today, now I have few things. I know d, I know t, and I know initial velocity. Is these three is enough for me to calculate g experimentally? Yes, we learned already from these three informations how can we reach the acceleration due to gravity g. Okay, so that we can use the displacement time relation. Can you please remind me about the displacement time relation? Yes, the displacement in the y direction, if I call delta y, yes, delta y is equal to velocity, initial velocity in the y direction. Yeah, it is v initial y t plus half a. In the case here, a is g, half g t square. Of course, this is a well-known relation and you did it many times. So here in this equation we know that the delta y is the distance traveled. So instead of delta y, if I place d and initial velocity, what is initial velocity in this case? 0, half gt square, right? So d is equal to half gt square. D is equal to half gt square. Or we can say d is proportional to t square. Why? Because g is a constant. That means d is equal to a constant into t square. Or mathematically we can write d is proportional to t square. So right now, what is our plan? Our plan is to reduce the distance d. So I have a d value, and the corresponding t. But we understand d is proportional to t square. So that means mathematically if I can calculate t square, it's fine, right? I have d and t square. One set of d and t square. What is my plan? I'm going to reduce this height to another 10 centimeter down. So the d is decreased. What will happen if I decrease the d? I have a second d. I decrease the d, of course the distance it travel is less, so the time will be less. I will get another time. Of course I can find time square. Now I'm going to repeat this with a different d. So I will have a set of d and time square. And of course we understand mathematically d is proportional to t square. Once we have these set of readings and we understand that d is proportional to t square, what we can do, as the way we did other experiments, we're going to plot a graph, and in which I'm going to plot d along the y-axis and t square along the x-axis. And what we learned, they are directly proportional, so that we will see that the data will be in a line. They are in one line, so that we will get a straight line. And once we have the straight line, the computer program is going to help us to plot this graph, and we can easily find the slope. What will be the slope? Slope is, this is the equation, right? D equal to half g t square. I plot this in the y-axis and t square in the x-axis. So the slope is y equal to mx, right? The slope is what? Half g. Or we can easily look into this, the slope, because we know that slope equal to what? Slope equal to delta y by delta x, right? What is delta y here? The y displacement. Delta y is d, and what is delta x? T square. D by t square, mathematically from this relation, what is d divided by t square? D divided by t square. D divided by t square is half g. Exactly, the slope represents half g. Now, after getting these readings, when we plot, we'll get a straight line, and from the straight line we can find the slope, and the slope will be equal to half g. Therefore, once we have the slope is equal to half g, therefore we can get g. What is g? 2 times slope. So we are going to find the experimental value of g, that is equal to 2 times slope. And that is our experimental plan, and we're going to do that here.
This is the free-falling apparatus. This device right here measures the time it takes for the ball to fall from this point up here, which is the sphere holder, down to the pad. So the time required for the ball to fall this distance is measured by this device. Now, in order for this device to work correctly, here we have 2 connections. As you can see, there are some wires. One connection on this plate and the other one on this brass screw right here. Okay. So when you insert your ball right here, this is how you will fix it in place. You will press on the shaft right here. Now the ball is held by the pressure of this plate, and then I want to hold it in place, so I'm going to tighten this lock. Okay. Now when the sphere is in position, it's a conductor because it's metal, so it will conduct electricity or electric signal between the 2 wires, the one on the brass screw and the one on the plate. Okay, so now the connection is established. That's how the device knows that the sphere is up there. The pad itself contains also 2 wires. One of them is welded to this portion of the pad, the upper portion, and the other one on the lower portion. When the ball falls down and hits the pad, the connection is established here, and then the timer will stop counting the time. Now, let's start by measuring the height of the sphere by measuring the distance between the bottom of the sphere and the top of the pad, because this is the distance that the ball will fall down. So I'm going to use the measure. Be sure that the measure is vertical when you take the measurements, and be sure that you are measuring the correct distance. One more thing, these measures, they have two scales, one in centimeter and the other one is in inch. So be sure to read the correct one. In my case, the distance is 67.5 centimeters. 67.5 right here, okay? Now, for this distance, we want to measure the time required for the ball to fall this 67.5. So in your table, you will write 67.5 centimeter for the distance. Now to turn on the timer, I'm going to turn or move this switch to the gate position. Okay, and make sure that it is reset. If there are some numbers here, you can press on the reset button and it will reset again. Now we have the sphere in position and we want to take our first trial. So remember, first we need to measure the height of the sphere. To do this, I'm going to measure the distance between the bottom of the sphere, for example, and the top of the pad. So we will release the sphere by loosening the screw that holds this shaft in place. Remember when we fit it in place. Now I'm going to release it and the time should be measured by the device. So as you can see, the time is 0.3754 seconds. This reading will be repeated 3 times or as told by your instructor. So to repeat the reading, I'm not going to change the height, but I will reset the timer, put the sphere in place, and then release it again. Now the same reading is repeated 3 times, and then the average is calculated. After this, we're ready to move on to the next trial, in which we need to use a different height. Now I'm going to change the height by loosening this screw that holds the assembly in place. Change it a little bit. And then put my sphere again. Now the distance between the bottom of the sphere and the top of the pad is measured again. Now it's going to be a different value. As you can see here, it is now exactly 63.0 centimeters. And then you repeat the same process again. The sphere will be dropped from this height 3 more times, okay, 3 times. And then you take the average, then you change the height once again, and so on.